Great, thanks for coming. And for those of you that missed the first talk, this is the second talk for the day, and this one's a little bit more advanced, so you can feel free to fall asleep if it's beginning to bore you or confuse you. Same caveats if you saw the first talk. Most of my experience is Williams. I'm not an engineer by qualifications. The topics we're going to talk about here, same thing, electrical fundamentals. I'll skip over that because I ran a little short on time last time, but it's essentially the same fundamentals. Inputs, outputs, switch operation, what is the matrix, diagnostics, problem solving, and other examples of multiplexing before we finally reach the summary. And as Chase said, please hold all questions until the end. So what is the matrix? Well, this is my little attempt at humor here. Do you really want to know what it is? Yes, the matrix is everywhere. And actually, that is kind of true because in a lot of machines, the matrix really is everywhere. But unfortunately, you can't be told what it is. You just have to see it for yourself when you open up the machine. But without further ado, you can dismiss my crazy humor. Okay, so electrical fundamentals. We covered this earlier. Basically, voltage, matrices operate on DC. Switches are low voltage, they're 12. Lamps, the lamp matrix is 18, it's a little bit higher. But even though it's 18 because of the strobing nature of matrices, which I'll get into later, lamps and the lamp matrix are actually rated at 6.3 volts, even though it's 18 as converted. Everything here is because it's DC, is relative to ground. I've already covered this, potential. Note it's all about the potential difference, not the actual difference. The potential difference is the path to ground potential. Again, the building analogy from the previous talk. The key here, though, is that, and the reason why I stress and emphasize potential is because when sensing switches, it's the potential that is sensed. The 12-volt potential corresponds to a switch is either open or closed. A 0-volt potential is typically in this case closed. But again, we'll cover this further with optical switches where the sense is actually inverted. If there is no path to ground, the potential is high. If there is a path to ground, the potential is low. And by using the terms high and low, we can avoid using 12-volt or 18-volt or whatever. It's either high or low. So when I look at a machine, and this is more generic, when I look at a machine, I see them in terms of mechanical, electrical, inputs and outputs. I don't think of switches, lamps, display, whatever. I just think, is this an input, is this an output, is this mechanical, is this electrical? Inputs are switches are just inputs. The system reads them as inputs. There's nothing to output to a switch. You can't physically close a switch. It's a read-only state. Solenoids, lamps and display are output. The software controls it, tells it to do something, and you get a result. It's a display on the screen, a lamp lights up, or a solenoid energizes. To break down displays further, they can be either numeric, or dot, and that's the progression throughout history. Numeric was the first iteration of displays. You'll see them in early Williams. Then they went to alphanumeric, and then they went to dot. And now they've gone to LCD screens. This presentation will focus on inputs, switches, because that's often where people generally see a problem. If you've got a problem in the lamp matrix, the lamp won't light correctly, who cares, the game still plays, right? If you've got a problem in the switch matrix, the switch don't register, well, game don't play properly. Now you're unhappy. This is why I want to focus on switches. Switches in general, well, let's look at the actual entity side of it. There are four basic types of switches that you'll see in machines. They're your simple mechanical switches. Those are leafs, typically 2-lug, or those micro switches with the switch body with that little actuating device. And those are either 2 or 3-lug. And we'll get into the differences in the lugs and the terminals and nomenclature a little bit later. Magnetic switch, which is otherwise known as a reed switch. This is where you move a magnet, or the change in the magnetic field causes the contacts, which are magnetically related, to either close or open by virtue of the change in the magnetic field. This is kind of interesting in the sense that, well, if you have a solenoid and you energize the solenoid, if you put a reed switch next to that, you can close the switch. And therefore, you can actually get feedback on the state of the solenoid without actually tying into the high voltage circuit. You could put the reed switch on a low voltage circuit, detect the presence of the magnetic field from the solenoid energization, and operate on a low voltage, thereby completely avoiding any high voltage danger. That's essentially an instance of the use of a reed switch. An electrical switch, that's otherwise known as an eddy switch. You see them in some games. This is where the change in the current flow is altered by the presence of a body that induces electromagnetic current is detected by an IC, and that change is sent back to the system either as the switch is opened or closed. An example of this is the Star Trek or Theatre of Magic outlane. When the ball comes near the outlane, the eddy sensor is triggered, and then the system responds by applying a magnet, in the case of Tom, to catch the ball. And, of course, the ubiquitous in Williams games, optical switches. These are light switches. There's a beam of light. The beam of light is either interrupted or not interrupted, and if it's interrupted, then it's one state, and not interrupted the other. And the reason why I'm choosing carefully is because the sensing of the state is typically inverted to the normal mechanical open and close. The thing with Williams machines to be particularly aware of is that optical switches are often characterized and called optos, but they're two different kinds of optos. There are discrete optos, which are those little white and black plastic housings that you see with a photo transistor and the LED. Those are driven by an opto board, and they always occur in pairs. What you'll also see is often these little tiny boards that have slotted optos on them, that have interrupters when a device comes through in a certain orientation and interrupts the beam. They are optos, yes, but they are driven and controlled separately. So often people will say, well, this opto doesn't work, and someone will say, well, go check the 7-opto board, when in fact what they're really talking about is a slotted opto. And a slotted opto is not controlled by the 7-opto board. So they've just given you some information that will not help you. This is the reason why I'm trying to bang home this point here, that there are differences, and not all optos are the same, even though they behave the same. Oh, switch operation. So this is huge big blurb about switches and all the different types and all the terminology that you'll see. Switches have poles and throws. A pole is a circuit that is switched. A throw is whether it's is the switch pole output opened or closed. For a mechanical switch, a switch is closed when the contacts touch. The switch is open when they don't touch. The definition here with resting state is really important because the nomenclature, which you'll see a little bit further, is normally. And normally is defined as the resting state, how the switch is when it's not actuated, acted on by a magnetic field or whatever. It's the resting state. Most switches have one pole. They just control one circuit. They're either opened or closed. A switch can have two throws. It can either be one contact that's opened or two contacts, one that's opened and one that's closed, and that's what's described here. One throw is SPST. You'll see that terminology used. You'll also see it used to describe relays. Relays are just switches that are controlled by an electromagnetic coil, which pulls contacts one way or the other. A two throws is SPDT. And the reason why I talk about this is you'll see later with wiring. Some switches only have two lugs, and a third lug is introduced for other purposes, and some switches have three lugs, and that third lug is used for other purposes. There's always a common terminal. It's always labeled C. The other two terminals, NC and NO, normally open, normally closed, to get resting state. And the terminals are labeled on a micro switch. You might not be able to see them as you get older, like me, but if you put a magnifying glass in front of them with a strong light, they are labeled. So this is what you'll see in a wiring diagram or a schematic, and it actually helps to represent what a switch is. You can see here on the left that that is an SPST switch. There is one circuit that's switched, and there's only one output state. It's open or it's closed. But the closed state is the only one it really cares about when the switch's contacts actually touch. But that's not what that shows. It actually shows it open because it's normally open. The one on the right is an SPDT. It's a single pole double throw. Again, there is that common terminal, but one of the contacts is normally closed where the switch is closed, and the other contact is normally open when the switch is open. When the switch is triggered, that shifts, so that line that you see 45 degrees to the top right actually goes 45 degrees to the top, to the bottom right, and these contacts switch as to which one's actually open or closed. However, the terminology is still the same. The normally closed one is now open when the switch is actuated. The normally open contact is closed when the switch is actuated. Remember, normally equals resting state. The terminals don't switch based on whether they're closed or open. The nomenclature stays the same. Switch operation. Oh, so different switches operate in different ways, and I touched on this a little bit earlier. Mechanical switch is purely contacts touching. Magnetic switch corresponds to change in magnetism. Electrical switch corresponds to changes in electromagnetic induction. And an example of this is actually if you line up at a traffic light, you'll often see those little wires in the street just before the traffic light, the square that's buried in there. That square is one big giant inductor. And it's detecting the presence of your car that is one big giant piece of metal. And that change in current flow is detected and says, oh, look, a car just lined up at the stoplight. I need to change the light. That's why at 1 a.m. in the morning when you're driving home, you line up at the red light, it suddenly changes to green because it can see you there. It's the same principle. It's just a magnetic switch, an electrical switch detecting a magnetic change. And an optical switch, as we discussed earlier, is the optical beam interruption. The definition of open and closed depends on the type of the switch. As we said, switch will either read 0 or 12. Most mechanical, magnetic, and electrical switches are open. Again, optical switches are normally closed due to the nature in which they operate with the optical beam. And the logic needs to be inverted. And I actually don't, I kind of feel uncomfortable dealing with optical switches because of the inverted logic, because like you, I look at things physically. I try not to look at things electrically. Okay, so let's start getting into the guts of this. What is a matrix and why use it? Because clearly it adds complexity, because people post questions about how does this matrix thing work all the time? Why don't you just keep it simple? The technical term for a matrix is multiplexing. It's using it's transmitting data in a switched manner. The primary reason to use this is to reduce wiring requirements. So if you have everything that's directly wired as a one-to-one switch, you're going to need 2 wires for each switch, one that goes into the common terminal and one that comes out from the normally open terminal. So if you have 64 switches in a machine, that means you're going to need 128 wires, and that's a heck of a lot of wires and a heck of a lot of different colors that you're going to need to determine which wire goes to which switch. Unless you're Atari, where every color of your wiring is white. It also means that you need to have 128 connection points for all of those different wires. So enter the switch matrix. Each switch requires only 1 wire per column and 1 wire per row. Everything is wired in parallel. 64 switches means you only need 16 wires, 8 columns and 8 rows. And that also means you only need 16 connection points. And it also means you only need 16 different colors. And that's part of the reason why. But it does add complexity. And by virtue of a matrix, it does add a diode requirement. And I'm not going to go too much into the diode the reasons why the diode is there, other than to say the diode should be this and it needs to be in this place. And I can discuss that with you later if you really want, but it's kind of a little bit beyond the scope. So everything there also applies to the lamp matrix. 8 wire colors for 8 lamp rows, 8 wire colors for 8 lamp columns. Exactly the same thing. Wiring conventions. Okay, so most switch usage is SPST-NO. All the switches in the switch, any switch that's in a matrix, not a direct switch, they are all wired the same way. The white color wire goes to the non-banded end of the diode, the banded end of the diode goes to the common terminal, and the green wire comes out from the normally open terminal. They're all wired the same way. This is a problem that a lot of people don't realize. Oh, well, the diode doesn't matter the direction, right? The terminal, we could wire it to the C or the NO. It doesn't matter. All the terminals are the same, right? No, they're not. This is why I'm going to the trouble of trying to help you understand that they're not the same, and they are labeled this way for a reason. There's a blocking diode, again, talked about. The diode is necessary due to the strobing nature of the way the operation works. Diode operation is beyond the scope. Switches not in a matrix do not require a diode. So an example of this is your coin door has switches that operate enter, test, up, down, or the left coin shoot or the right coin shoot. Those are direct switches. They do not require a diode. And if you look on your machine, you will see they do not have a diode. Same is true for flipper cabinet opto switches and flipper EOS switches in Fliptronic machines. Those are direct switches. They do not require a diode. It's only the 8x8 switches that have a bunch of green and a bunch of yellow wires that are matrix wires that need that. So in the older Williams manuals, this is what you would see for their switch matrix diagram. And it actually does show all 64 switches wired the way they should be wired as a typical wiring diagram. But it's kind of a lot. It's confusing. It takes up a lot of space. It doesn't really add to much. So Williams changed it. And they started doing this. They started putting this at the top right corner of their matrix chart. And this is exactly the same thing. The white wire goes into the non-banded end of the diode, goes to the banded end of the diode, goes through the switch to the green wire. It's exactly the same. Always wired the same way. In fact, if you look here, you'll see this theory of operation on how the switch matrix works. Well, guess what? It's the same thing. The white wire comes off the CPU board, goes to the non-banded end, goes to the banded end, goes to the switch, goes to the green wire, comes back to the board. We'll discuss this part of the switch matrix a little bit later. This part is the sensing part. Okay, so we covered a little bit of this too. Wiring diagrams show logical connections. The matrix charts, they're all logical connections. The physical connections may be different. That's why I have these things here, and I'll give you examples of it later, because often what you see here is not what you see in the manual when you look at that chart. It's just like it's well ordered in the manual. It's not well ordered in a wiring bundle. The key to remember here is everything's in parallel, and that means that order does not matter, because every point in a parallel circuit is connected with another point at that same point. 1, 2, 3 is the same as 2, 3, 1 is the same as 1, 3, 2. Doesn't matter. So this is what a logical representation of a switch connection would look like. One wire comes in, gets connected in parallel to one of the switches, and so on. It goes all the way around. And the same with the other side. One side's row, one side's column. This is simplistic logical connection because there's no diode there. This is what it actually looks like. There's a row wire that comes in, it goes to the diode connects to one end of the terminal, the common terminal. The other end, the coal wire comes out from the normally open. And I just repeated this so you can see. And I will publish these slides later if you want to look at it in your own leisure to try and help you understand it. But the key here is to understand that logical does not equal physical. When you're looking at how it works, read the logical. When you're looking at how it's connected, you have to look at the physical. State processing. So the matrix has an 8x8, 64 entries, switches or lamps. Each axis is a column or row, can control 8 entities at a time. So the way the switch matrix works, at least on a WPC machine, and it's true with System 11 as well, is the software will enable one column and then read 8 rows. It reads all 8 rows at one time. It then says, okay, turn off column 1, go to column 2, and do the same thing. Read another 8 rows. Turn off column 2, go to 3, and so on, all the way up to column 8. Once it's done that with column 8, it goes back to column 1. So this part here, think of it as lanes on a bridge. I want to expand on this a little bit. So I'm going to keep it simple. Instead of using 8, we'll just use 4. But it's the same thing. It could be 8. So think of this. I have 4 roads of 4 lanes coming into a bridge. And the bridge itself only has 4 lanes on it. So now I've got 4 roads of 4 lanes, but all 4 of them can't fit on the bridge at the same time because like, I've only got 4 lanes. So what do? I say, well, okay, you in road 1, you 4 lanes of road 1, you can come onto the bridge now, and I'm going to charge you a toll or whatever it is. I'm done with road 1. I say, okay, now all you 4 lanes on road 2, you can come onto the bridge now, and I'm going to charge you a toll. And the same goes on with row 3 and row 4. And that's really all that the switch matrix is. It's just processing 8 items at a time, 8 times over. It's allowing 4 cars onto the bridge for 4 lanes 4 times over. That's all it is, and it's done in a round-robin fashion. Now, not all the cars may be occupying the lanes. So if there's no car in the lane for that time slice, then the switch may be open or it may be closed, depending on what your definition is. Or if you want to think of it in more concrete terms, the car can either be a forward or a not forward. And if the car comes through and it's a forward, then it's closed. And if the car comes through and it's a not forward, then it's open, right? But that's the principle. Everything is treated in a round-robin fashion. And this is what I'm saying. The nature is strobed. Okay, so the consequences of this. Well, you can only read 8 switches at a time. So that means the software just doesn't see individual switches. When it reads a row of 8 switches, it sees all 8 at once. It doesn't see switch 5. It just says, give me the 8, all of them, and it records that. But it only records that 8 at one time. Again, if it wants to see a different column, it's got to switch to that column and read 8 switches at that time. The key here to understand is that the switch matrix itself is typically only processed once all 8 columns are read. Otherwise, it's only seeing 1/8 of the state of the world. It really wants to see the whole state of the world. So it'll read all 8 columns, all 8 rows in each of these 8 columns, build up that matrix of 64 switches, and then say, okay, now which switches are open or closed? And the software will then look at an individual switch in that case. But the individual switch itself will not be detected as a failure because it reads 8 at once. So this is also true with lamps. The software will enable 8 lamps in a column and then choose to ground whichever of the lamps it wants on 8 at a time. Disable that column, go to the next column, ground those 8 lamps. It's exactly the same. It's the nature of the way the matrix works. 8 at a time, 8 at a time. And there's that final. Think of 8 roads of 8 lanes merging onto a bridge. It's the same thing if you want to think in concrete terms. Diagnostics. So matrix problems can be diagnosed using the software diagnostics. Not enough people use their game diagnostics. They say, this switch doesn't work. Well, have you tried testing it? And often, when you run the diagnostics, a byproduct of what the software reports will give you an idea of where the problem may be. Diagnostics will report single switch by scanning the matrix. Again, as it scans it all and it shows what the 8x8 shows. Same with single lamp. This point I can't emphasize strongly enough. Always differentiate between board and playfield causes. These 2 lines are another more key lines. It is not possible to find a board problem in the playfield. And it is not possible to find a playfield problem on a board. If you do not do this differentiation and you immediately assume that it's some diode or wiring or whatever issue and the problem is on the board, you will have spent a lot of time doing absolutely nothing. Always differentiate between playfield or board. And there are tools that will help you do this. If you don't have the tools, you can use an alligator clip. Run the software test, use an alligator clip. And the key is to remember that software deals with 8. It always deals with 8. So if there is a failure, you will see a failure in a group of 8. That is just how it works. And those last 2 are the same. Failure of an entire column or row are going to be board related. Failure of an individual switch or lamp is going to be playfield related. Okay, so it's almost never a failed diode. Well, what does this mean? Well, oftentimes you'll see people ask, this switch doesn't work, or I have a problem with this switch, and someone will say, oh, well, that's a broken diode, or that's a failed diode. And the answer is, no, it probably isn't. Much as you might think that it's an individual switch, and therefore it's a failed. No, it isn't. The switch matrix diode rarely, if ever, fails. I've never seen one fail. Simply never seen one fail. However, what often happens is it's miswired. It hasn't necessarily failed, it's been miswired. Someone has decided to replace this switch, and they think that, well, you know, all the terminals are the same, C, NC, NO, who cares, it's just a terminal, we'll just connect a wire there. The diode, that silver band there doesn't mean anything. The diode is usually one of two things, incorrectly oriented or connected to the wrong terminal. And as I said, excuse me, all the switches are connected in the same way. There is no change. Once you know the pattern, they're always connected in the same way. These last two ones are kind of me being a little bit facetious, poking the bear. There are many ways to wire the switches on the playfield. You know, C, NO, diode, who cares where. There's only one way to wire it correctly so that it works. And that's according to the wiring diagram. And it's always wired the same way. I can't stress that enough. So, measuring the diode. Okay, so someone says the diode's bad and you want to prove it to them, or you want to convince yourself that, yeah, the diode really isn't bad, I just want to measure it. Well, the problem is that the diode is attached to a micro switch, and unfortunately, it cannot be measured at rest. And the reason is that the diode is connected between the C and NC terminals. The fact that it is connected between C and NC means that, well, it's normally closed. What that means is that there's continuity between the C and NC terminals. So when you measure that diode, you're not measuring the diode, you're just measuring the continuity. The DMM is always going to report that this diode is shorted because it's not measuring the diode, it's measuring the C and NC terminal. And this is why you cannot measure a diode in circuit, for the most part. However, you can, in the case of a switch matrix micro switch, measure it in circuit. What you do is, you close the switch, and when you close the switch, that NC terminal now opens up. But when you measure the diode in that case, you're actually measuring the diode because that NC terminal is no longer closed, it's open. And what the DMM measures is actually the diode. You can also disconnect the diode off the switch, but well, that involves heating up the tab and running the risk of burning the switch and melting the plastic and whatnot. It's just, don't do it. If you're going to do that, just take the diode off, put a new one on, or just get a new switch. So this shows you how to measure the diode diagrammatically. The left side is the resting state. When the switch is open, the actuator is sitting there resting around. What you're actually doing there, as you can see, is when you test between this point and this point, or this point and this point, what you're actually measuring is not the diode, you're measuring that NC terminal. When you close the switch, it flips to this, and now what you're measuring between these 2 points is the actual diode. This is why it actually does work, but you have to remember to close the switch. It is often rare, though, that you can test a diode in circuit. You cannot test a flipper solenoid diode in circuit, because you will always measure the solenoid winding. And the solenoid winding is always a certain number of ohms that is not an open line, and the multimeter will report that the diode is continuous. So it's not always the case, but this is one where you can, if you know how it works. So problems. Ground short row X. You've probably seen that a few times when you turn on your machine. It's like it says, ground short row 5. It's like, what? What's going on? There's nothing connected to ground. You measure everything, there's nothing connected to ground. Well, this is a manifestation of a failure of 8. Again, the entire row has failed. It is a failure of 8. This is a matrix problem. Not all 8 switches in your row 5 are connected to ground. This is a failure of 8. So again, the software grounds column 1 and reads 8 rows. It proceeds to columns through 2 through 8, and it repeats the cycle. If the column is shorted to ground, then the 8 rows will always read closed. So I think, no, I didn't do this. So I'll get into the details of this in just a little bit, but I'll keep reading through this slide. When one of the in this example, when the switch in row 2 is closed, it will report as closed for every row if there is a failure in the grounding mechanism. The grounding mechanism is that U20, ULN2803, which is a Darlington transistor array, which people in the know often call the switch matrix fuse, because it blows a lot. And it blows when you touch solenoid voltage onto the switch matrix, because that IC is not rated to handle solenoid voltage. I believe it's rated to handle 50 volts DC. Solenoid voltage is 70 volts DC. You put 70 volts through there, it's going to blow. And that's what happens. So why does this ground short show up? Well, let's think about it this way. I have a switch in row 2 that is closed. It's just physically closed. That's the nature of what it is. If the CPU thinks, the software thinks it's grounding column 1 and now reading all 8 rows, then perhaps in column 1, row 8, it really is closed. Okay, that's a true result. It really is grounded. But now, if there is a permanent short on one of those columns, the CPU thinks it's going to ground column 2, but in fact, it's going to see a ground through that permanently shorted column. So therefore, it will think that all switches on that row 2 are going to be grounded. So here let's take, for example, ground 4 is permanently shorted. It's always shorted to ground. But switch 1-4, column 1, row 4 is closed physically. Software says ground column 1, read the switch. It reads as closed. Turns the ground off column 1, says now ground column 2. It tries to read the switch. Now, if everything were working properly and column 4 were not grounded, it would say, well, that switch is opened. But now there is an errant path to ground through that column, and it thinks that row 2 is actually closed, even though it's not. And it goes through the entire 8 columns, and it says, well, row 2 is closed in every column. Every time I switch column, row 2 is closed. What's going on? And then it reports ground short, row 2. And you look at this and go, well, that's not right. How can that be? Switches in row 2, all of them aren't shorted to ground. They can't be, because you look at them physically, they're not shorted to ground. But the reason is the way the matrix works. It scans each one, and if it detects it's unable to detect an errant path to ground by a shorted column. It says, I'm going to enable column 2, and I expect all the grounds that I read, all the switch state that I read to be related to column 2. But if I'm reading a column state from 4 because it's grounded, because it's shorted in hardware, it doesn't know that. It only says, well, I tried to ground column 2, and this is the result I got. I tried to ground column 3, and this is the result I got. And because column 4 is not under software control, it will read that as a short. That's why you see this all the time. It's very common. If you ever see this ground short, column, row, whatever, bet your bottom dollar it's going to be that ULN2803, the U20. This is the reason why, again, if you understand how the matrix works and how the software reads it, you can try and piece together the puzzle of why the software is reporting what it's reporting. Broken wire. So the matrix charts show everything in a logical order. When you read it, you'll see row 1, row 2, row 3, row 4, and all the way up to row 8, column 1 all the way up to column 8. And it's nice and ordered because, everything goes from 1 to 8. The ordering in a chart makes it really easy to find because it's sequentially incrementing numeric order. However, the physical order in a machine does not necessarily correspond to the logical order that you see in the diagram. So as I said here, the charts show connect 1 to connected to 2 to 3. Since the wiring is in parallel, the order does not matter. You can connect things in the order 1, 2, 3, 4, 1, 3, 4, 2, 1, 4, 2, 3. It doesn't matter because everything's wired in parallel. The order is not going to be the same. And this is where people get confused because you point to them on a chart that shows them the logical order of where their failure is. They look in their switch matrix wiring and the order doesn't correspond to the same as what they see in the chart. And you have to remember, it's parallel wiring. The order is not the same. And a broken wire will exacerbate this even more, and you'll see that in the upcoming diagram. These problems require diligent inspection to find. There is no magic cure, show me where it is. You have to look, you have to correlate the order. So this is my attempt at trying to illustrate what I mean by order does not matter. So if I have a bunch of switches here, and the nomenclature standard is column row. So switch 1, 1 is column 1, row 1. Switch 2, 1 is column 2, row 1. Switch 3, 1 is column 3, row 1. That is how WPC uses nomenclature. What you'll see here is, if you think of it in a logical order in the diagram, like in the chart, you'll see 1, 2, and 3. So if the break in the wire happens at that point there, switches 2 and 3 will not show up because they're just broken. The wire continuity doesn't happen. So if you look at the diagram below where, well, they're still wired in parallel, so it's still valid, it's completely legal, electrically legal. However, if the break happens where you see there, then all you'll see is a break in 1 and 2 and 3 will register. But it doesn't matter because you can tell someone, well, the break has to be, switches 31 and 21 register, but switch 11 doesn't. Therefore, the break has to be at the very beginning, right? Because it's number 1, right? No, the answer is no, because the order does not matter. What you see on the top is, yes, the order matters. Switch 11 is broken. Switch 11 works. Switch 21 and 31 do not work. But again, order does not matter. I can't stress that enough. So here are some other examples of matrices. They don't have to be 8 by 8. You commonly see 8 by 8 because, well, 8 is a power of 2, and these things are run by computers which are based in binary, 2 to the power of 3. But you can also have other things, numeric displays, like on Williams System 7. Those are two 4-bit BCD digits by 16 strobes. You will notice, however, that those numbers are still powers of 2. But it doesn't have to be 2 to the power of 3 by 2 to the power of 3. An alphanumeric display that you commonly see is 32 segments by 16 strobes. So the way those displays work is the segment pattern is lined up, and then the columns, the digits, are strobed. And then the next segment pattern is lined up, and then the next strobe. So you have 16 digits or characters across, and it's just segments, strobe, character 1, segments, character 2, segments, character 3, and again, same thing, all the way up to 16, loop around, do it again. That is how an alphanumeric display works. Dot matrix, it's actually the same thing. It's 128 pixels across, 32 rows down. However, the pixels are not 128 signals. The pixels are clocked, which is why it says they're clocked column bits, and I don't want to get into clocking at this moment because that's digital logic. Solenoids. Solenoids are actually also, believe it or not, in what you could call a matrix. It's multiplexed. And I'll show you the diagram in the schematics that actually explain that, yes, this is true. You may have 32 or 28 solenoids in a WPC machine, but they're actually multiplexed. They're strobed. Because multiplexing is just a way of overlapping signals. It doesn't matter what the signal is. It's just a way of using a channel of 8 in different ways with multiple tags or signals or whatever. The goal is to use less signals. So if again, 128 wires or 16 wires, which would you rather have? That's the nature of the matrix. So here's the example of why solenoids are actually considered a matrix. The way the software works is it says, I'm going to deal with solenoids in groups of 8. 1 to 8, 9 to 16, 17 to 24, and 25 to, in the case of Williams, to 28. The last 4 solenoids are not used. So it has 8 data bits here. D0 to D7, and those are the actual data bits. Then it says, okay, so I'm going to put these 8 data bits on the bus, put them on the bridge, put them in a lane, whatever you want to, however you want to think of it, and then say, okay, I'm going to trigger the signal for Sol 1. So those 8 bits are destined for Sol 1, groups 1 to 8. So it says, which of these do I want? Let's say I want us to energize 5. It lights up D4, because it's 0-based, and then says Sol 1. And Sol 1 says, Sol 1 says, I'm just listening on the data bus for the Sol 1 signal. When it sees the Sol 1 signal, it pulls the 8 data bits off the bus and says, oh, you want 5 because you lit up D4? No problem, I'll do it. But if you don't light up Sol 1, it ignores it. So in this case, let's say you want to light up 13, which happens to be 5 plus 8. It will set the same bit 5, D4, on the bus, but instead of lighting up Sol 1, it will light up Sol 2. There's a chip there that's listening on the data bus that says, oh, Sol 2, that's for me. It then takes the 8 bits off the data bus and says, oh, bit 5 is on, let me light up, energize solenoid 13. But you can see this is just another form of overlapping 8 signals directed to 4 different groups. It's just an 8x4 matrix. It's just a different way of looking at it, but it's still the same thing. The consequences of this is that you can actually look at the failures and see failures in different ways. So for instance, if you go to a machine and solenoid 5 doesn't work, and solenoid 13 doesn't work, and solenoid 29 doesn't work, is it 20, 21st? Yeah, 29, and solenoid 21 doesn't work, you can see that those are all multiples of 8 mod 5. So if I take that number, I divide it by 8, or take the modulus by 8, it's always a remainder of 5. And that tells you this is a pattern where it's just like, well, 8 bits, and go light up Sol 1, Sol 2, Sol 3, Sol 4. It tries to. Each of those guys listens and says, well, that signal, those 8 bits are for me, but the bit itself is bad. It's not changing to a 0 or a 1. And that's how you can see that failure. And the same is true for the lamp matrix. If you look at this, this power driver board header interface here, you'll see there's also lamp row and lamp col. And those same 8 data bits, believe it or not, are used to control the lamp matrix. So if you have bit 5 out, and you have one of these nice little 8x8 LED matrices, you'll see that col 5 doesn't work and row 5 doesn't work. And you'll instantly know that that data bit is out. Again, failures in groups of 8. It's the nature of the way this thing works. And I've gotten through this one much quicker. So implementing a matrix is a way to reduce the number of signals. Again, 16 wires is better than 128. The consequence of that is that only a fraction of the controlled entities can be controlled at any one time. That is what multiplexing is. It is, though, essentially a bunch of data signals, 8 bits in this case, and control signals. Who gets the who is this 8 bits of data for? Without latches, which is a form of memory, a matrix requires constant servicing or strobing. So if you look at the lamp matrix, or the switch matrix even, in terms of reading, it says 8 bits, column 1, 8 bits, column 2, 8 bits, column 3, and so on up until column 8. The thing with the lamp matrix is that it's momentary. That lamp in column 1 is only enabled at the time column 1 is enabled. As soon as you enable column 2, the lamps in column 1 are off. So how does this work? Why do you see the lamps actually lighting up? It works this way because it works so quickly, and your human eye is slow to respond, that the human eye will perceive it as actually on all the time, even though that lamp is actually being turned on and off really, really, really fast. Your eye doesn't pick that up, and that's why it can get away with it. It's a similar principle to things like video and interlacing. If you go back to the days of NTSC, interlacing is the same thing. It's multiplexing, right? Showing every half signal, every V vertical blanking. It's exactly the same thing. They all take advantage of the fact that your eye has some latency. Even in the alphanumeric displays are another example of this. If you use a camera, sometimes you can capture images at the certain state where your eye sees a totally seamless display. If you use a video camera, which captures at a certain refresh rate, it will see the strobing nature. Same with a dot matrix. Point your camera, take a video, watch the frames, you'll see it. It's just that your eye can't see the latency because it's slow. Always differentiate board versus playfield. Hammered that home enough, I think. Matrix failures manifest patterned, either data or control, like I told you, right? If that bit 5 fails, then everything that gets a signal for bit 5 is going to fail in bit 5. However, if the control fails, then all 8 of those controls, those signals being controlled, will fail. So for argument's sake, if sol 1 signal fails, then none of those solenoids are going to fire regardless of what's on the data bus. The signal's not getting through. The diagnostic, do not guess randomly. Diagnostics must be systematic. You oftentimes see people say, well, go to the switch matrix chart, figure out, write down which switches work, which ones don't, and people often look at that and say, oh, that's too much work, I just want the answer. It doesn't work like that. The matrix by its nature is complicated, which means you have to invest some work in it. And if you don't want to invest the work, that's okay. Ask somebody to come out and pay them for their time. Otherwise, learn how to do it yourself. Gather all the failures, look for it in a pattern, as I said, just work. And sometimes, this is the kicker, sometimes there may be multiple masked failures. You must always remember that the rule is that always look for a single point of failure. If you can find one point of failure that explains every sign or symptom problem that you're seeing, then that is the single most likely problem. However, that's true that may be the problem that's caused that you see, but once you fix it, you may unmask another problem that was masked by it. So don't assume that that's the case. There may be multiple failures, and it's just diligence, right? Switch matrix problems are common. They do fail. ULN 2803s fail. People work on their switch matrix with the power on and their short solenoid voltage. It's been done before, done again. So always be systematic about it. I can't emphasize that enough. And I think I'm early at Q&A. Any questions? Step on up to the microphone.
There we go. I have a question, and specifically, it relates to a WPC 89 game that I've been working on, and the tieback diode. So you're going through explaining like the brackets of them, but on a creature game that I'm working on, specifically the last solenoid, it's like on a flasher circuit, but I've never got quite a good explanation of what the tieback diode circuit is. And because that's on or related to the switch matrix, I'm wondering if maybe you can relate it to what you were talking about.
So, tieback diode, I hate to tell you this, the tieback diode has nothing to do with switch matrix.
Not at all, because
nope.
Essentially the issue that I'm having is a thing where this switch operates and it functions in the diagnostics where I can operate. It's specifically an up-down ramp where it goes both ways, but there's 2 switches from the board that operate it. So if I'm in the diagnostics, it works, but as soon as I operate it in the game, it fries something like
a solenoid.
The fuse is blowing out.
Okay, so if
I've been working on it for a while, but essentially I was just wondering if there was any connection between that and the
not with a matrix. What you're describing here is, and I think this was in my last talk about power. So a solenoid is what's called an inductive load. There is a magnetic field that is generated. Mm-hmm. A flasher is what is called a resistive load. There is no magnetic field generated. Every time you have an inductive load, a diode is required. Mm-hmm. Because what happens is when the current starts flowing, a magnetic field is generated. And once that magnetic field reaches an equilibrium or a fixed point, it starts pulling in the plunger.
I see.
Once you stop the current flow, that magnetic field is still present. Mm-hmm. And what happens? It collapses.
Yeah.
And when it collapses, by virtue of the fact that there's electromagnetic induction, it generates a current. but it does it in reverse.
Yeah,
And by generating that current in reverse, it generates a reverse potential difference voltage, and that spike is often 2 to 3 times negative.
Yeah.
So if you have a drive transistor that's rated for 100 volts, and you apply 70 volts DC across it to energize it, like Williams WPCs do, when that magnetic field collapses, you generate 3x negative the voltage. You're generating negative 210 volts. And your drive transistor is not rated for the negative voltage.
Yeah, and it's loud when it means like.
Yep.
It does the whole
And
thing.
as soon as that solenoid is no longer energized, it pops that transistor. When it pops it, unfortunately, it always pops it shorted. So it doesn't actually stop the current flow because the transistor is now shorted. The only thing that stops the current flow is your fuse blowing.
Yeah, and that's actually exactly what happened. It,
Right?
like physically exploded the first time I turned it on.
And when your fuse blows, it should stop it. Now, the problem is some people decide to put 20 amp fuses in their machine, and that generally takes a lot longer to blow.
Yeah.
And because it takes longer to blow, more heat is generated. And more heat is generated, more things start igniting. Fun and games. So your diode, back to your original question, the diode is not related.
Yeah. Thank you so much. I appreciate it.
Hi, Victor. So, really quick question: what is the frequency of running through the switch matrix? Like, how?
So that's a software implementation detail. I myself have actually not looked at the software, but I suspect it's done every millisecond on the IRQ.
Yeah,
If that makes sense to you. It's probably done in the ISR, the interrupt service routine, because the ISR runs on the interrupt, the IRQ is generated by hardware on a timer. So the IRQ generates an interrupt, the software takes the interrupt, then executes the ISR does all of its work, and then returns back from interrupt where the regular program operates. I suspect that's how it's done, but again, I didn't actually write the code, so I don't know.
Thanks. And by the way, to your point about diodes, I did have a diode problem in a game I was working on. It wasn't installed.
Okay, that's another case.
And so lights just, some lights that were not supposed to be on were on at the same time.
Yeah, and that's the backflow of current, but that's beyond the scope of what I wanted to talk about.
Right.
But again, that comes back to the point. A diode is required for everything that's on a matrix, regardless of switch or lamp.
Thank you.
No other questions? Okay, well, I hope this helped because when I was first confronted with the matrix, it was mind-blowing. And when you break it down, it's really just 8 things at a time, 8 times over, ad infinitum. Thanks for coming. Enjoy the rest of the show.